So for this assignment, the data set I am working on is predicting whether a patient has diabetes. So first of all, I will try to randomize the data points so that there is no inherent bias. So I'll create a separate row for that. At first, I'll see how many rows my existing data set has, which is over 250,000. So I'll select ran between from 1 to 300,000 so that I have a sufficient number of random numbers to sort from. Then I'll select all of them. I'll choose paste as values so that they don't keep refreshing over and over again. And then I'll sort them in a certain order, let's say ascending order, so that I can choose the data from this. So, so for this particular training set, I will use top 10,000 datas. So I will be selecting them. Okay. So I have selected the top 10,000 datas, and now I will select only the ones to see how many true cases there are, and then I will paste them. I can see that there are 1400 true cases, so I'll select 1400 false cases as well, so that the data is equally distributed in terms of whether a patient has diabetes or not. Once I'm done doing this, I will create a table out of it, and so I'll create this table and I will assign it a certain name. In this case, it will be training underscore raw. Once I'm done doing so, I will create a set of dummy variables. So I have already prepared the set of formulas that I will be requiring. Most of them are quite simple, as you can see. These only take the datas from the table I just built. There are a few which are not as easy, however. So right now, what I'm doing is the dummy variables were encoded on the basis of the original raw data set, which was diabetes.raw, but I now changed it to training underscore raw so that all the formula they change and so do all the values. Now, once I'm done doing so, here's a quick idea on what I did, especially on a specific field such as the BMI value and when is. So here are the formulas for the table. As you can see, that there are a lot of variables, 41 to be more specific, excluding the intercept, of course. And most of them are dummy encoded, and some of them have certain formulas which are relevant. For example, the moderate and overweight categories have separate formulas. Now I will select all of these and paste the values on a separate data set so that they don't get corrupted. Then I will create a set of model coefficients. Once I'm done doing so, I will create a linear combination row where I will show the formula, which is, okay, before that I'll create the table. Once I'm done doing so, I'll create a row for linear combination, and now I will put in the formula, which is sum product of all the model coefficients. So I'll name all of the model coefficients a certain name, and then I'll do the sum product with the certain columns as well as the model coefficients. Once I'm done doing so, I'll create another row, which will be the sigmoid transformation. Now, the sigma transformation essentially encapsulates all of the linear combination values from 0 to 1, the formula for which is the e to the power of x of where x is the linear combination over 1 plus e to the power of x, again, where x is the value of linear combination. Once I'm done doing so, I will create another row for the table, which will be the row for probability. Now, the row for probability would have a formula which is sigma transformation times the outcome, which is in this case whether a patient has diabetes or not, plus 1 minus the sigma transformation and 1 minus whether the patient has diabetes or not. So let me fill out the formula. Okay, perfect. All right, looks good. Okay, once I'm done doing so, I will create another column, which will be the column for the log likelihood. Now, since the multiplication of all the probabilities would give us a very small number, instead, we would do a summation of all of the log likelihoods. So the formula for the log likelihood is pretty similar to the formula of probability, but in this case, there will be logarithmic scalings on the sigma transformation values. 1 second. Looks good. All right. Yeah. The logarithmic scaling will only be on the sigma transformation. Once I'm done doing so, I will create the sum of the log likelihoods, which will be the sum of the entire row in this case. All right, perfect. Now, our objective using the solver would be to maximize this log likelihood, where I will change the variable cells, which are the model coefficients in this case. Since I would use the evolutionary method, I would have to change certain constraints. So I'll constrain the model coefficient to be between 1 and -1. Okay, then I'll change the solving method to evolutionary, and I'll change the maximum time without improvement to 100 in order to give me a better value. And then I'll hit solve. So this should give me a proper value. This isn't scientific, so let me convert it to general. Okay, pretty good idea. Now, the conditional formatting gives us a very basic idea on which variable affects our model and how does it affect it. For example, high BP, high cholesterol, these will be massive indicators, whereas age will have variation and all sorts of other stuff. But this gives us a basic idea on how each variable affects the model. Okay, now once we're done with this, we will move on to the next part, which is the test set. So again, I will go to the raw data set and I will select. So in our training module, there were 2,800 different data points, not data points, different rows. So in this case, we will be selecting 25% of that, which is 700. So once I'm done doing so, I will rename it as test underscore raw. And similar to the training module, I will also change the domain coding variables on this as well. I will use the method I used before, which is essentially renaming and replacing the formulas. So I'll select show all the formulas, then copy the entire thing so that it's convenient for me. And then I'll paste it onto a separate sheet where I will again select show formulas and then I'll replace it. Okay, so the we need to find out training underscore raw and we need to replace it with test underscore raw. Okay, 47 replacement complete. Perfect. Once we're done doing so, we will paste the entire thing as values onto a different sheet and create a linear combination of all of the data points here along with the model coefficients. So a sum product essentially. And then we would move on to creating the sigma transformation here as well. So the formula would again be the same. So it would be the e to the power of x over 1 plus e to the power of x, where x is the linear combination value. Okay, sounds good. Perfect. All right. Now, once I am done doing so, I will create the ROC curve. So the maximum of the sigma transformation will be necessary in this case. So I'll refer it from the previous sheet. So maximum of the sigma transformation from the test sheet, and the minimum as well. Now, this would indicate the probability cutoffs. So I'll write down probability cutoffs, and I'll also write down the false positive rate and the true positive rate, FPR and TPR respectively. And I will select the minimum, and then I'll fill it with a series. I'll use the step value of 0.01, and I'll stop at the maximum value, which is 0.93 in this case. The series will be in columns and it will be linear. My bad, 1 second. All right, so doing the same thing. I mistakenly chose a different. Okay, perfect. Now I'll figure out the false positive rates and true positive rates for each of these probability cycles. For that, I will be using the let formula. So here, at first, I will be selecting the false negatives for the false positive rate, the formula for which would be count ifs. The sigma transformation values of the test check data sheet should be greater than or equal to our given probability range or cutoff, which is in this case equals to A6. Also, the test check diabetes prediction or the diabetes binary values should be equals 0. All right. I will also find out true the true negatives, which will be count if, my bad, count if of the diabetes binary variables of test check, whether it's 0. Finally, I will divide the false negatives from the true negatives, and this should give me the false positive rate value. Once I'm done doing so, I will do the same for the true positive rate. In this case, I'll copy paste the same formula and make a few modifications. So in this case, it will be true positive and all total positive, and both of these values of test check diabetes binary values would be 1, and I would need the ratio. So it will be in this case dp over total p, and then I'll drag it down. Okay, once I'm done doing so, I will create the ROC curve. So inserting an ROC curve out of the two rows, and the ROC curve would be a scatter plot. So yeah, so as we can see, the ROC curve looks quite good, and it seems to be a very reasonable predictor of whether a patient may or may not have diabetes.